Hello, everyone. In this video, we're going to talk about the August 2021 Prelim Problem 2. And what we have here is a birth and death type process, meaning it's not quite a birth and death process. And I'll tell you where it becomes not a birth process as we kind of describe what's going on. So we have a population, and the population increases only due to immigration with a constant rate lambda. So in this population, no one is born or no cells divide. The only way the population increases is if individuals come in from outside the population. This is, again, a constant rate lambda. And so that's telling you that it doesn't depend on the current number of people in the population. The next thing we have is that the death rate per individual is some mu. And it is true for a continuous time Markov process on a discrete state space that the inter-event times must be exponential. We get that from the Markov property. And so this is really saying that the time for an individual to die, take any individual at any instance of time, that individual has an exponential rate mu amount of life left. And the final thing here is that the entire population is wiped out by disaster or disasters that come according to a Poisson process with some rate lambda. I'm sorry, with rate nu. And so what are we following? X of t is the population size at time t. So this is right here. This is the part that makes it not exactly a birth process. A birth process in any instant of time can go up by 1 or down by 1 or stay the same. But we can actually have the entire population wipe out. So we can make moves from, say, population size of 10 down to a population size of 0 in an instant. So it's almost a birth and death process, but the actual birth and death process doesn't allow for moves like that. Okay, so let's get into the problem. In the first part, we want to write down a generator matrix. A lot of people, myself included, usually call this Q, and it's made up of entries Qij, which denote the infinitesimal transition probabilities, the rate of change of those transition probabilities of moving from state I to state J at an instant of time t in a time homogeneous process. So it doesn't really matter what time t we're looking at, given any fixed time. If the current population size is I, it's the infinitesimal rate of change to the state J. And I think I'm going to try to write this down, maybe not with a matrix, we'll see, but the elements here. So given we have I people in the population, we can go up by 1, and that will happen with rate lambda, the immigration rate. And this will hold for I equals 0, 1, 2 on up. And then let's talk about going down by 1. Now, this is going to be different depending on whether or not I is 1 or not 1. You'll see what I mean in a moment, but first let's look at this for I equals 2, 3, 4 on up. So this means that we're going to have a death. And we currently have I people in the population, and they each have an exponential amount of time with rate mu before they die. So in this picture, I've got 5 people in the population, and those exponential clocks are racing. So the next overall death from the population happens after the minimum of 5 of those exponential times, and that is an exponential random variable with rate 5 times mu. In general, if we have I people in the population, the death rate is I times mu. And again, that holds for I equals 2, 3 on up. We have to treat I equals 1 a little differently. So if I look at Q1, we've got the Q1, 2 taken care of, but we can go from 1 down to 0. And there's two ways for that to happen. So we have like one individual in the population, and that individual has a lifetime that is exponential with rate mu. And when that individual dies, we can go down to zero, or we can go down to zero if the entire disaster comes and wipes out the population. And that happens with a rate nu. So the minimum of those two exponential times is when the population is going to drop by 1. And we have, again, an exponential with rate mu and an exponential with rate nu. And the minimum of those exponentials is exponential with rate mu plus nu. The other interesting rate parameter we have is we can go from any state I down to 0. So I already took care of the case where I equals 1. So this is going to hold for I equals 2, 3, 4 on up. And that happens when the population just gets wiped out at times of a Poisson process with rate nu. Okay, so the Qij that are not already defined here they're all 0 if j does not equal I. So this is like, we're not going to go from a population of size 2 to a population of size 8 in an infinitesimal amount of time. And then the diagonals of the matrix are negative numbers such that they make the row sum to 0. These are the negative of the sum of the rows, the individual row. So if we're talking about the II diagonal, then that's going to be the negative of the sum of the other elements in row I. So I think that's good. I think you can leave it there. But if you want to make the matrix, let's try to write this down. Got our state space over here and over here. So if you're at state 0, the only place you can go aside from staying at 0 is state 1, and that will happen with the constant immigration rate lambda. And we can't go from 0 to 2 or 3 or 4, etc. in an infinitesimal amount of time. And because the rows have to sum to 0, then the 0, 0 entry must be negative lambda. So now if we're starting with one person in the population, we can go up to 2 people in the population with rate lambda. That's the immigration rate. We can't jump by more than one person at a time. So the rates as we go from 1 to 3 or 1 to 4 or 1 to 5, etc., those are 0. We can go from 1 down to 0 with rate mu plus nu. So that's really a 1 times mu, if that makes the pattern seem any easier. That's I times mu, where I is 1. And finally, the diagonal entry is going to be the negative of the sum of the other rates in the one row. From state 2 or 2 people in the population, we can go up to state 3 with rate lambda, and we can go down to state 1. Now that's going to be a death in the population, and there's 2 individuals racing to die. And so that rate is going to be 2 times the exponential rate for each individual. We cannot jump up to 4 or 5 or anything like that, but we can have this disaster that wipes out the population and brings us down to 0. And that's going to happen at rate nu. Finally, this diagonal entry is going to be whatever we need to make the row sum to 0. Okay, so one more, because that's where you really start seeing a pattern. From state 3, we can go up to state 4 with some rate lambda. That's the immigration rate. We can't go up to state 5 or anything above that. From 3, we can go down to 2. So this is going to be the I mu, but I is 3, so it's going to be 3 mu in there. From 3, we can drop all the way down to 0 with rate nu. That's the disaster happening in the population. In an infinitesimal amount of time, we can't go from 3 to, say, 1. So that rate is going to be 0. And then here is the 3, 3 diagonal. That has to be whatever makes the row sum up to 0. So that's going to be the negative of lambda plus 3 mu plus nu. And now we do really have a pattern going. These are all going to be nus down here. These are all going to continue to be zeros. The diagonals here are going to keep increasing. We've got this 2 mu, 3 mu. The next one's going to be 4 mu. The above the diagonals are all going to be lambda. And then on the diagonal, so for example, on the fourth diagonal, we would have negative lambda plus 4 mu plus nu. So we're done with part A. In part B, we want to know if this chain is reversible with respect to some probability measure pi. Now, reversibility in discrete time means that we would need pi I pij, that's the one-step transition probability, to equal pi j pji for all I and j in the state space, which is 0, 1, 2 on up. But this isn't discrete time. We have continuous time. In continuous time, it doesn't make sense to talk about the probability of transitioning from state I to j in one time step because there is no such thing as a time step anymore. So in continuous time, the reversibility equation becomes pi I qij equals pi j qji for all I and j in the state space. This chain is irreducible. We can get from any state to any other state. For example, we can get from state 7 to state 13 by having 6 births, or we can have a birth and a death and then another birth and something that, or we can go all the way down to 0 and then back up to 13. We can get everywhere from everywhere else. Because the Markov chain is irreducible, that tells you that the pi's, if there is a stationary distribution or limiting distribution, this tells you that the pi's are all going to be positive or non-zero. These are probabilities, so they're definitely not going to be negative. But in the long run, you can be in any state I with some positive probability. So we want to know if whatever this, we don't know exactly what this pi I is, but if for any such pi I, can we get this to hold for the given qij's that we already wrote down? And the place where this is going to break is by the asymmetry of dropping down to 0 by disaster. So for example, I can go from state 5 to state 0 with rate nu. That's the disaster wiping out the whole population. But I can't go from 0 to 5 in an infinitesimal amount of time. So you can see that pi 5 q50, if we want this to equal pi 0 q05, we are in trouble because this pi 5 is greater than 0. This q50 is nu, that's greater than 0. The q05 is equal to 0, and the pi 0 is something greater than 0. So on the right-hand side, we have 0, and on the left-hand side, we have something greater than 0. So we can't do this. We can't find any such pi that's going to be reversible or have detailed balance with respect to the generator matrix. So no, the process is not reversible. It does not have detailed balance with respect to any stationary distribution pi. And that's the end of part B. Okay, in part C, we want to look at the expected value of x t plus some infinitesimal time unit h, given that xt is I, and we want to write this with little o of h expressions. To write this down, I think maybe we're more familiar with little o of h for probabilities. And so let's write some of those down first. So given we're starting at I, in h units of time later, we could go up to I plus 1, we could go down to I minus 1, we can go all the way down to 0 if I minus 1 does not include that 0, and we can stay where we are. So given xt is I, this probability is a constant rate lambda times the length of the time interval h plus little o of h. And if you're writing this in birth and death process notation, this is lambda sub I, the birth rate of the population when there's currently I people there. But people are coming in at a constant rate independent of the population size. So now let's try to go down by 1. And I think we're going to have to worry about whether or not I is 1. So in the I equals 1 case, the probability that will drop down to 1 minus 1 or 0, that happens in 2 ways. We either have a death with rate mu or 1 times mu, or we have a disaster wiping out the population at rate nu. Those are both exponential amounts of time, and the one that happens first is the minimum of the 2 exponentials. So this is going to be, the rate is going to be the sum mu plus nu h plus little o of h. And this happens if I equals 1. To drop down by 1 when I is anything else, that doesn't come from the disaster, so there's going to be no nu in here. This rate is going to be I mu h plus little o of h, or the probability. So this I mu is like a mu sub I. And in fact, this mu plus nu is mu sub 1. If you're using that kind of birth and death process notation, that's supposed to be the rate of death when there's currently 1 person in the population. So in this process, we don't just have births and deaths. We can drop the entire population down to 0 in an instant. And we already have taken care of this in the case where I is 1, because then this was 0. But if I is anything other than 1, this was not 0. So we haven't taken care of that case yet. This is going to be just in this amount of time, we're going to drop down according to a Poisson process with rate nu, and that is independent of the population size. So we're going to get nu times h plus little o of h. And this is going to hold if I equals 2, 3, on up. And finally, we can stay where we are. So given the population size at time t is I, the probability that it's still I at an infinitesimal amount of time later. So let's consider the I equals 1 case first. How do you stay at 1? You basically don't go up to 1 plus 1 or 2, and you don't go down to 0. And so we get 1 minus the sum of those other probabilities. So we get 1 minus lambda plus mu plus nu h plus little o of h. So that came from this with I equals 1. So there's the lambda h. And then this with I equals 1. And that's where the mu plus h comes in. And we have to add those and subtract from 1 to get the probability of staying where we are. Okay, so this is when I is 1. And actually, I think the others are going to follow the same pattern, so I don't think there's a reason to do this piecewise thing here. But for any I greater than 1, the options are to stay where we are. We want to not go up. So we're doing a 1 minus like a complement. We want to not have a death, which happens at rate I mu. The death rate per individual is mu, but for the entire population, it's I times mu. And we want to not have a wipeout. So this is the same form as it was for the others, so we don't need to have written that piecewise. I guess I should consider still I equals 0 separately here because we can stay at 0. So in the case where I is 0, the only way we move away from 0 is if we have a birth with rate lambda. So this is going to be 1 minus lambda h plus little o of h. In fact, you don't have to reason through all of these. So the probability of going from I to j in t units of time is supposed to be a delta ij, which is a 1 when j equals I and a 0 otherwise, plus a qij h plus little o of h. And these qij's we already wrote down. So q0, 0 is the negative lambda. It's one of those diagonal entries. So again, we didn't have to reason our way through this. We could use the fact that we already wrote these down to get all of these. But this isn't what the question was asking. It wasn't looking for a probability. It was looking for this expectation. So let's go. The expected value of the population size at time t plus h, where h is very, very small, given the population size at time t is I, I am going to just write this right now for I equals 2, 3 on up. We can drop down to state 0, and that will be the probability that we have dropped to 0 in h units of time, given we started at state I, and we already have it written down, but who cares because we have a 0 out front. Plus, we can go up to I plus 1, and that's going to be the probability x t plus h is I plus 1, given x at t is I, plus we can drop down by 1 with the probability of dropping down by 1. And finally, we can stay where we are. So we can go to state I, and that's times the probability that we go to state I, given we started at state I at time t, and h is supposed to be so small that the only way to go from I to I is not to move. So I'm going to try to collect all these terms. And obviously, we don't need this first term because it's multiplied by 0. And I'm going to go work that out on the side. So I'll be right back. Okay, so if we put that all together, I did that off video. That's a lot of work, especially scrolling back and forth to get all those conditional probabilities needed to write out this conditional expectation. Hopefully it will be easier for you because you'll have papers spread out in front of you and you'll get to see lots of parts of the problem at one time. But I do get this expression for the expectation, and this does hold even when I is 0 or 1. So from this, I'm going to rewrite this as, and this is the tricky part, or I should say the non-natural part. I'm going to rewrite this in terms of just the random x of t without a value plugged in. And that is going to be equal to x of t plus lambda h minus x of t mu plus nu h plus little o of h. And usually when we have something like this, we want to solve a differential equation. You see that t plus h there, but the conditional stuff is making this weird. So I'm going to take the expected value of both sides. On the left side, by the law of iterated expectation, we have this result that says the expected value of x given y is the expected value of x. So I'm going to use that on the left-hand side. And after I take this expectation of this conditional expectation, I'm left with the expected value of x t plus h. And on the right side, I've got the expected value of x of t. And then the expectation of this, that is constant or non-random. And so we just get lambda h minus, so this stuff can come out of the expectation. I have mu plus nu h, expected value of x of t, and this has no random stuff in it. So this is going to be the expected, or I'm sorry, it's going to be, so this is just going to be little o of h. And now I'm going to take this and subtract it to the other side, And then I'm going to divide both sides by h. So I get the expected value of xt plus h. So now I'm forming that derivative looking thing over h. And with what's left on the right side, and remember I divided by h, I just get like lambda here. This term went to the other side already. This term is going to get divided by h, so I get minus mu plus nu expected value of x of t. And this last term gets divided by h. The little o of h term gets divided by h. So now I'm going to let h go to 0 on both sides here. And on the left side, I have the derivative with respect to t of the expected value of x of t. On the right side, I have lambda minus mu plus nu expected value xt, and this last term goes to 0. So this is what we're left with. And to solve this differential equation, I'm going to move this to the left-hand side. So I have the derivative with respect to t of the expected value of x of t plus mu plus nu expected value x of t equals lambda. And I'm going to multiply through by the integrating factor e to the mu plus nu t on both sides. So just get all that stuff over here. And after doing that, on the left side, I have the derivative of the product e to the mu plus nu t times the expected value of x of t. And on the right side, I have what I have. So I'm going to integrate both sides with respect to t. On the left side, the fundamental theorem of calculus, I'm just undoing that derivative. I get e to the mu plus nu t expected value x of t. And on the right side, I'm actually going to have to integrate this, and I get lambda over mu plus nu e to the mu plus nu t. And these are indefinite integrals, so both sides should be plus a constant, which I can put all on one side. So plus some constant c. And now I can solve for this expected value of x of t by moving this over to the other side. We get the expected value of x of t is equal to lambda over mu plus nu plus c times e to the minus mu plus nu t. And this constant c has to be finite. That's the, plus c on any integral. If you take the derivative, that will zero out. So when you go in the reverse, you can, get rid of any constant, but you would not be taking a derivative of infinity. So this c is, when you do plus c on any integral, is assumed to be finite. And with that, we can take the limit on both sides as t goes to infinity. You get the expected value of x of t, and this is going to go to 0, so we get lambda over mu plus nu, which is the final answer. And as the hint suggested, there's more than one way to do this problem. I'm just doing this way in this video, but as long as you get the right answer, you probably did it right in another way. And one of those ways could be kind of maybe reasoning your way through the expected population size as this sort of ratio. And another could be solving for pi using the equation pi q equals 0, which is going to be a lot of work. And then you'll get a vector of probabilities, and you can compute this expected value of x of t at any time t out in the limit. And that's a lot of work. So I'll see you in the next one.